The next one is stationary waves formed in a stretched string. So when a string of length L is attached rigidly to these 2 points, this length is L and its mass is say m, therefore linear mass density mu is m over L, and there is a tension that is say T in this string. Now we are going to pluck this string exactly at the center. Therefore, there will be a vibration set up. The first vibration will look like this. First mode of vibration, as I am plucking exactly at the center. Two nodes are present at these two fixed points and one antinode is present. This is the least possibility. Between any two nodes, there has to be one antinode. Therefore, now we can make use of the formula for transverse wave, speed of transverse wave in a stretched string, that is V equals square root of T by mu, tension by linear mass density. And also I know the relationship with velocity, and that is V equals wavelength into frequency. So I can write down frequency in this example. I will call it as nu naught, as responsible for fundamental harmonics. So nu naught is equal to V by lambda. And now I shall find out lambda in terms of the length of this string. Since there is only one loop, this length corresponds to half of the wavelength. So L equals lambda by 2. I can represent lambda as 2 times L from this equation. So the expression for fundamental frequency changes to, in the place of lambda, I will substitute 1 over 2L into velocity is square root of tension by mu. So this is representing the fundamental frequency, or also called as first harmonic. Harmonic means it is multiple of fundamental frequency. If there is a number like say 100 hertz, that is fundamental. All the multiples of 100 are called as overtones. It need not to be actually an integral multiple, but all the integral multiples are called as harmonics. Now for the same length, I am producing two segments. That means three nodes are present and two antinodes are present. The whole length remains same, but wavelength is changed. Let me consider the wavelength to be lambda 1 and the frequency of this vibration is nu 1. And how lambda and L is related in this is L equals lambda, because there are two segments. Each segment is equal to lambda by 2. So lambda by 2 plus lambda by 2 is exactly equal to lambda. So length matches with the wavelength in second mode of vibration. This is second mode. This one was first mode of vibration. So I can write the expression for frequency nu 1 in this case as V by lambda 1, and that is equal to square root of or 1 by L into square root of T by mu. Or you can write this as nu 1 equals 2 times nu naught. So that means the first mode of vibration is exactly half of second mode of vibration, that is frequency. Or you can say the frequency of second mode of vibration is 2 times fundamental frequency. This is called as second harmonic, or first overtone. Why it is called as first overtone? Because it is frequency which is first obtained, or which is exactly integral multiple of fundamental frequency. Next one, let us see in the same length, the third mode of vibration. So you have three segments contained in the length L. Therefore, I call this new wavelength as lambda 2 and frequency as nu 2. So how L is related to lambda? L is equal to, this is one complete wavelength and another half wavelength. So it is 1.5 wavelength. So 3 by 2 lambda 2, or I can write lambda 2 equals 2 times L by 3. Therefore, nu 3 is equal to 1 over lambda 2, that is 1 over 2L divided by 3 into root of T by mu. Or you can represent nu 3 as 3 times nu naught. It is third harmonic or second overtone or third harmonic. It is 3 times fundamental frequency. For any nth mode of vibration, you can write nu n equals n into nu naught for nth harmonic. That is general expression. So this is about the standing wave produced in a clamped wire at both the ends, right? Now, what is the application of this? Or we have a device called as sonometer. The sonometer is actually a same setup in which we can vary the distance between fixed points of the string. So there is a law for transverse waves in a string, and the first law says that it is actually based on the equation frequency nu equals what happens 1 over lambda into root of T by mu, and we know that lambda is proportional to length of the wire or the string which is stretched between 2 points. So the same equation is formulated into three laws. First law is called as law of length, and it says that the frequency of vibration is proportional to 1 over length only if the tension in the string and linear mass density is kept constant. So nu is inversely proportional to length. Or you can also write nu L equals to constant, or you can say nu 1 L1 equals to nu 2 L2 for the same wire at equal tension and linear mass density. The next law is called as law of tension. So it is evident that frequency is proportional to root of T if length of the string is maintained to be constant and linear mass density remains constant. And the third one is law of linear mass density, and it reads that nu is inversely proportional to square root of mu, keeping tension and length of the string constant. In all these three experiments, the general condition is that temperature should not change, as length of the wire can vary with the temperature. So using this relationship, we can solve problems on frequency of a stationary wave set up in a string which is stretched between 2 points. Third point, as a consequence of superposition principle, which is beats. Beats are actually produced due to superposition of two waves moving in a same direction with a small difference in their frequency.